So I'll be talking about how you can tune ABAP with hardware mechanics. We will soon specialize this frame because I will mainly be focused on RAM access, but the topic is still very interesting. So, short introduction, this is my name. I'm an ABAP developer and my specialty is performance tuning. Yeah, that's practically it. We will be talking about memory bandwidth and why it matters. So we'll be talking about RAM access latency and why that matters. And I tried to make this talk as practical as possible, so we always have a chapter called Reality Check where I challenge myself. And at the end we'll have some practical applications of how you can actually implement this. The coffee machine is running. So, hardware mechanics. I want to start off with when is this relevant, because last time I presented this was quite an issue. So this is only relevant if you have no easy wins anymore. All read table statements are fine, all loops are fine, you have no object spamming, you have an infrastructure that is actually there and supports you. Or you're tuning very frequently accessed ABAP code, like some magic API that is built in 100,000 times in your system. Or if you have the luxury to design a project from scratch and you can actually model the data structure from 0 up, then this could also be quite interesting to you. I have a highly complex example which we will adjust through the presentation. And this example mainly consists of one algorithm and one data structure. This is my data structure. Who doesn't know what an internal table is?
Internal table.
Internal table, ABAP. Doesn't know. Okay, an internal table is like a list. So this is my structure. I have an ID, integer 4, and I have 1 million lines of these, and this is how it looks in ABAP. Very simple. A highly complex algorithm is I have a loop, and this loop adds 1 to this ID field. So I generate 1 million lines, and then I check how fast I can traverse this, this internal table. So for each item, we add 1 to the ID counter. Pretty simple. There is an initial runtime, and this will be our benchmark. This is what we will compare our changes to after we actually do them. So our initial runtime is something around 50K, 51K microseconds. Now, Alex here is always my scapegoat when it comes to this, because he always comes with me new requirements. And my problem is, he gave me a new requirement, and that is that I have to transport stuff around. I have to have a payload. Now, I don't actually need that payload, someone else does, but he's further down in the application, so I don't have to do anything with this, but I still have to transport it. So this is my new internal table, 1 million lines, and my payload is a character 100, so that's like 200 bytes. Now, I don't expect my runtime to change, but you know, I have to check. And inconveniently, somehow, for some strange reason, I'm slower. And I don't understand why. Now, I try to blame him, but he's pretty good at talking himself out of trouble. So in the end, it's my fault. And I don't understand why. So components of structures impact performance of a loop, even if we do not access them. So the magical question is, well, why is this? How structure access works. This is almost structured, almost language independent, so if you're coding in C, C#, Java, this is all the same. This is my structure, my ID, and my payload. Now, in my loop, I am accessing one structure component. That is my ID field. But what I get back is the whole structure. This is something that my hardware does for me. It's actually good that it does this, but it's not so fortunate if I don't know that it is doing this. So the problem is this weighs around 4 bytes, and this weighs around 200 bytes. So now I went from transporting lines with 4 bytes of memory allocation to 204. Now, my data is transported from RAM to my CPU by the bus system. And as every infrastructure, the system has a maximum transfer rate. That means that if I want to transport more, I'm not as fast anymore. Also, my data is fetched in bulk. That's called contiguous memory access. So if I start with the first line, my hardware actually supports me and it prefetches the next 8, 9, 100 lines, depending on how wide my structure is and depending on how the capacity is. So information density actually matters, and that's the main problem with this. So I went from transporting around 4 to 204 bytes without actually doing anything, and my algorithm still works the same. And just what I'm doing is I'm just clogging up my infrastructure with useless junk. Now, refusing to transport information to transport that information faster is not a viable solution. I can't go to my business analyst and say, you know what, I tuned our system, it's freakishly fast. We have no attributes anymore. Real applications have a lot of attributes. That means we have, usually in SAP systems, we have very wide structures, like 1K, 2K, 5K, even 8K is nothing unusual. For some strange reasons, these applications also have to be fast. And they also have to be scalable, which kind of contradicts the way we model our data, because if we are pushing around 10 kilobytes per line, that's not very lean. And that puts a lot of pressure on our infrastructure, and that way we become, we aren't as fast anymore, and we also have scalability issues, because our infrastructure from a certain point on can take the amount of punishment we're inflicting on it. So how can we actually reduce consumption without refusing to transport any data around? What we will do is we will apply a little trick. Now I say trick because it is one. We will actually split our structure. We will have this part and this part. So what we will do is we will hide our payload field behind a reference. Now reference weighs only 8 bytes. That means that the green part now weighs 12 and the payload still weighs 200. And this is how we could elegantly implement it in ABAP. We just say, okay, we outsource our payload field into a separate structure, and the structure is not boxed. So it is handled implicitly like a reference, but we can access it as if it was an integrated structure. So this is what our data structure actually looks like now. Our algo still hasn't changed. And this is our new runtime, so we went basically back to where we started, plus minus 3K. Now, this is how it works. You all know this part, we access one structure component, but instead of towing with us this whole payload field, we only get the pointer, which is live. Now, so we can hide information behind references, and we can thereby reduce our memory bandwidth consumption. So now my magical question is, well, should everything be behind a reference? I mean, I found a working solution. Where are my problems? Who thinks that hiding everything behind a reference is a good idea? Who thinks, no, it's a really bad idea, please don't do that? Who has no opinion at all? Yeah. At first, I didn't know this myself, so when I tried this, it surprised me. So this is my new structure. I have two references. One is pointing at the payload, one is pointing at the ID. Still 1 million lines. I traverse through it, and my runtime blows up. I'm like factor 8. Now this is quite a disappointment because I was really keen to share this new solution, but it obviously doesn't work. So what happened? We're accessing this structure in a bulk fetch. Now this part is already known. But the problem is that my algorithm doesn't actually care about the references. It cares about the ID variable, and that it doesn't get in that bulk fetch. Which means, when I access it, I have to go in a second time to access the reference variable. Now from the developer standpoint, so what? I mean, it's hardware, I give a command and it abides. What the hell? That's not so easy, unfortunately, because we have a thing called access latency. Everyone knows what a cache is? Level 1, 2, 3, yeah? Who doesn't know? So depending on where your variable lies, or where it is buffered, you face certain penalties which you pay for accessing it. The farther away you get from your CPU, the more cruel this punishment becomes. Optimal condition is something in level 1 or level 2 cache. So you've loaded it already into cache and then you're reusing it, or it has been prefetched and you're using it for the first time. Yeah, every time we access to a penalty, we pay, for a reference, we pay some kind of penalty. The best case, we're just 10 times slower if we compare level 1 cache access to RAM. And in the worst case, it's 100 times slower. Although I have to say, the worst case is not this worst case, because the worst case is your machine is overloaded to such an extent that you're facing consequences much more severe than this. If you have like a gazillion processes operating on one system and it's a main host for 1,000 virtual machines, this can become quite common. Unfortunately, our algorithm has a second flaw, that is that we are actually collecting those penalties. So for every line in our internal table, we go back to RAM, pay a penalty, get the value back. Next line, pay a penalty, get the value back. So we're actually ignoring all our hardware's capabilities to support us by prefetching data. And we're telling it, well, I don't actually care what you prefetch for me, you're just prefetching instructions where I can find stuff, and now I'm hopping around and RAM collecting latency penalties. So outsourcing behind the reference can reduce bandwidth consumption and improve performance, but if I actually touch it, it blows up in my face. So how do I apply this? I mean, I have certain behaviors that provoke a different response in performance. So there must be some kind of way to use this. Does anybody have an idea? Anyone?
Well, reference stuff which you don't need, and don't reference stuff you actually need to really work on and change.
Yeah?
Perhaps to reference the stuff grouped by application area. So if you have a component that uses 2 or 3 fields, group them in a structure and have them load only when that component is used.
You're right. That's exactly what the practical example would be. So this is the most simple way I can put it. I have my loop, which is known. I have my stupid add statement. And here I have some kind of condition. Now, the important thing is to analyze that condition. The value that I'm analyzing has to be not referenced, so it has to be part of that structure which I'm loading, so I can actually get something by the prefetch mechanism. My payload is behind the reference. So if I pay for every 1,000th access, the amount I pay for the access latency penalty is much lower than what I would actually pay in memory bandwidth costs. So my initial runtime, if I don't hide it, is 164K. And if I just box my payload. I'm down to 91. Now, this stuff scales. Your applications are usually very complex. You have thousands of attributes, hundreds of classes, even more, many different data structures. So the way you design your application, the way you have your data modeling done, actually lays the foundation for your baseline performance. So if you tune it then you'll get a really, really good performance out of your system. I have seen applications in the financial sector which had a very funny and unusual behavior. When we overloaded the system, and we overloaded it like ×2 or ×5, we could never bring the CPUs to 100% work. We just couldn't. And we increased work processes, we parallelized more and more and more. And they were all between 60% used and 80% used. Does anybody know why?
Was the RAM the limiting factor, the bandwidth? The RAM?
Yeah, they were all waiting for data. They were all pure OO, and the way object orientation was implemented there was through a chain of reference accesses. So you had a chain of like 16 references behind each other. So now I can imagine that the main thing that you're doing with that kind of application is just hopping through RAM and collecting access latency penalties, and that your CPUs are bored as hell, even though you overload the machine by the factor of 2 or 4 or 5, and you can overload it by infinity, it wouldn't change anything. So this is my last slide. I hope I'm in time. Yes, probably. Yeah. I had to cut out my initial demos because I thought I didn't make it in time, but yeah. Q&A.
Why do I need an internal table of millions of entries? I'm wondering.
All clients that I saw had some amount of data, and 1 million in one internal table or 100K was not something that was considered to be a lot. 1 million is actually not that many. For example, we have a business partner system that has 26.7 active business partners, million active business partners.
Yes, in a table, but in an internal table,
Yeah.
in the memory, that's another. My first approach would be, what about the selection criteria? Reduce the size of the internal table. That's the first step. If it is a HANA, I would then much more doubt about this approach. If the internal table is already that large, well, then I guess that might be a valid way of tuning. But my first question would be, why do I have such a large internal table? What are you doing with so many data in memory?
It doesn't matter if I have 10,000 sets in an internal table or 1 million for this mechanic to work or not work. Why I chose 1 million is because if I have like 600 microseconds or 1,300 microseconds, I can't measure anything properly. That's the reason why I picked 1 million. But your baseline approach would be to model your data structures in a way that could scale. If you have only 1,000 data sets in an internal table at all, or 500,000, then this maybe doesn't apply to you.
Well, I think, can I add something to this discussion?
Yeah.
Or kind of just shouting in.
Yeah, I think what you said is just completely valid, and that's something you should ask, or the developer should ask himself, and that would be probably really a good first approach. But if you are at the point where your internal table basically has a reasonable size which it needs to have, you still want it. You still might have a performance issue, and then maybe this being applied can solve it. Or let's say, as you said, things are summoning up, so you have this at various places, and it just impacts performance then when you sum all these little places together up. But obviously you're right, and after your first initialization has been done and you're still facing performance issues, then he kicks in with his kick-ass solution and saves the day.
Or the table is small afterwards.
Yeah, and then still you might want to add this to not have like leveraging over and over at certain places these small pitfalls of performance overheads.
But the main problem with stuff like this is, as I mentioned in my second or third slide, this is actually done when you have no easy wins anymore, or you have a very homogeneous performance trace of positions. So you don't have that one point where you can go in and say, okay, if I reduce this by 50%, the day is safe. This is something that needs to be done from a baseline level with almost every data structure if you actually take it seriously, or if you have the problems that are big enough that you have to do this.
Just to add to this, we do have actually an application, a potential application of these box components in our environment where we have a very large display data structure, but only certain groups of users tend to use various fields of these. So we were rather excited when box components were first introduced. But as you can see from these numbers, we quickly found out that any gain that we would have seen would be essentially lost in the noise. So we are simply not having that kind of performance gain in this area. We have, if you remember my talk from last year, we have very different kinds of coding problems altogether. So you really need to come down to a point where you can really use this, where you will see this difference. You have to basically have solved every other problem.
Yes, that is exactly right. This only counts when you have everything done and you have essentially, like most standard modules, are like tuned to the last bit. No retables that are important that are slow, yada yada yada. But when you need that last kick for an API, this is something that you can actually apply.
So I'm curious, do you see this approach being applied in the standard ABAP code and
No,
being shipped
never.
by SAP?
Never.
Good, thank you.
Actually, because this is hard. Because this brings you, and this might be a counterpoint to myself, but this locks you into a dependency. So if you start remodulating your data structures according to this, you will lock yourself into a certain way of structure and into certain dependencies, and if you have to have some kind of unusual changes, then it's an obstacle you will have to overcome. It depends on what kind of performance you need compared to the data you're processing.
Perhaps as an addendum, you're starting to add a new level of model that you need. Beforehand, you need a model of a function model. What does the application actually need to do? What data do I need at which point to do something? And what you need to add to leverage this kind of performance boost is to add a behavioral model. How does the user actually use part of the application? In which combination will I access the data throughout the flow of the application? And I can believe that that is quite difficult to find out in an application that is as versatile as what we are seeing every day.
Machine learning that has
Yeah, and to add to this, when the requirements change, because nowadays we're all agile and the new use case needs us to access some stuff which is boxed before, and now we need to pay the cost of dereferencing it, then things change again, and you need to overthink this, maybe your model. So yeah, you really have to look when does it apply and even change it if it doesn't apply anymore and the costs are too high on other grounds. Cool. Thanks for explaining boxed to me. I saw it, I never used it. I didn't graph it, but now I understand it. Thanks.